Pluto is a mysterious and faraway celestial body that was once considered a member of our nearby planetary family. However, constant and disturbing announcements from prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the limelight with a startling revelation. They suggest that this cold world is on a possible severe collision trajectory with Neptune. Yet, how could this unfold, and what might be the repercussions of such a colossal event? Are we witnessing a rapid trend, an immense, impossible-to-ignore phenomenon, or is there another reason for this impending major incident? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, previously classified as a planet before being redefined as a dwarf planet due to its unusual orbit, continues to be a topic of interest and research in the astronomical community. Recent evaluations by renowned experts indicate that Pluto's orbit is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potentially perilous collision between these two celestial bodies, which could pose a serious threat to Earth. But how could an event of this nature occur? Pluto's orbit around the Sun is unlike that of any other planet in our neighboring planetary group. Takes an astonishing 248 years to complete one full orbit. Since its discovery in 1930, it has not even completed a single full revolution. However, the intrigue does not end there. Pluto's course is characterized by its highly elliptical shape, significantly deviating from the nearly circular orbits of major planets. What makes Pluto's orbit even more peculiar is its tilt, angled at 17 degrees to the ecliptic plane. Compared to other planets, Pluto's path is considerably steeper. This tilt and elliptical nature introduce layers of complexity to its orbital behavior. One of the most captivating aspects of Pluto's trajectory is the point where its orbit intersects with Neptune's path. For approximately 20 years in each orbit, Pluto actually approaches the Sun more closely than Neptune. This contradicts what we might expect based on their positions in the solar system. This raises a natural question. Why hasn't Pluto collided with Neptune? The explanation lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, cosmologists sought to clarify its unusual trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path was distinctive due to its steep inclination. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune, further illustrating the complexities within celestial mechanics. The three-body problem in astronomy examines how three space objects, like Pluto, Neptune, and the Sun, interact and influence one another through gravity. Predicting their future positions based on their starting points and mutual gravitational pulls is a challenge. In Pluto's case, this dilemma explains how its orbit remains stable despite its interaction with Neptune's orbit and the Sun's gravity. Two key concepts, mean motion libration and vertical oscillation, help clarify this puzzle. According to astrophysicists, mean motion libration is what keeps planets in their orbits. In the case of Pluto and Neptune, this means that whenever Pluto is at the point where it crosses Neptune's orbit, it is approximately 90 degrees away from Neptune. This spatial separation prevents their orbits from converging. Vertical oscillation, on the other hand, refers to the movement of a celestial body in its orbit. In Pluto's case, when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial aspect is the VZK oscillation, named after researchers who studied how celestial bodies move in space. This oscillation describes how Pluto, Neptune, and the Sun influence each other's movements. The VZK oscillation helps explain why Pluto's orbit, despite appearing chaotic, maintains long-term stability. Although Pluto's orbit exhibits chaotic tendencies, numerical simulations conducted in the late 1980s demonstrated that its unique characteristics contribute to its long-term stability. Studying this chaos through virtual simulations has enhanced our understanding of how giant planets, such as Neptune, Jupiter, and Saturn, have influenced Pluto's motion around the Sun. Neptune also has a unique relationship with Pluto. For every 3 orbits Neptune completes around the Sun, Pluto completes too. This orbital resonance helps maintain Pluto's predictable trajectory. However, Neptune isn't the only planet playing a role. Jupiter's gravity also has a significant stabilizing effect on Pluto's orbit. In fact, Jupiter's gravitational influence alone is strong enough to keep Pluto on a consistent path for billions of years. Therefore, it appears that Neptune, Jupiter, and Saturn work together to ensure that Pluto continues to navigate safely through space without the risk of a collision. Understanding Pluto's orbit is crucial, especially in discussions about its potential collision with Neptune. Provides insights into the dynamic nature of our solar system. Pluto serves as an example of how even the most seemingly unstable orbits can achieve equilibrium through the intricate interplay of gravitational forces and orbital mechanics. This also highlights the importance of continued observation and research to deepen our understanding of our place in the cosmos. Space frequently forces us to confront celestial unpredictability, and the orbit of Pluto serves as a prime example of this eccentricity. The notion of orbital chaos, which refers to the delicate dependence of a celestial body's course on its initial conditions, is strikingly evident in Pluto's case. Even minor changes in the speed or location of the dwarf planet can significantly reshape its long-term orbit. The use of virtual simulations has proven extremely helpful for researchers working to comprehend Pluto's movements in space. These simulations utilize advanced mathematics to show how Pluto, along with other celestial bodies like Neptune and similar objects, exerts gravitational effects on each other. By adjusting minor details in these models, astronomers can observe how even small alterations can lead to substantial differences in Pluto's ultimate position. In the late 1980s, these simulations revealed truly fascinating information about Pluto. Despite the presence of stabilizing influences like magnitude and degree, its course may continue to be erratic and unpredictable. A minor variation in Pluto's velocity or location can result in a vastly different orbit over many years. Despite all this chaos, Pluto's orbit remains stable for long periods, billions of years in fact. This suggests that, while Pluto's orbit around the Sun may initially appear chaotic, there is an underlying order within it. Predicting future events, particularly involving unstable orbits like Pluto's, presents significant challenges. The intrinsic unpredictability of such systems means that long-term predictions are often fraught with uncertainties. While numerical simulations provide a robust method for anticipating and comprehending celestial bodies' future behavior, they also highlight our limitations in prediction. These models heavily rely on the precision of initial conditions and the intricacies they attempt to imitate. Even a slight error or distortion can lead to drastically different outcomes, making accurate predictions a formidable challenge. The chaotic nature of celestial orbits, such as Pluto's, serves as a reminder of the ever-changing and dynamic essence of the universe. Despite this, we have made considerable strides in understanding Pluto's place in space. Its case demonstrates the limits of our cosmic knowledge. The gravitational influences of the giant planets that orbit Pluto provide valuable insights into the broader dynamics of our solar system. The position of each planet can significantly affect the stability and trajectory of other bodies within the system. This raises an important question. Why do some astronomers continue to raise concerns about a possible collision between Pluto and Neptune, despite the complex forces working to prevent such an event? Neil deGrasse Tyson, a well-known astrophysicist and influential figure in cosmology, offers a unique perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson is famous for his role in reclassifying Pluto from a planet to a dwarf planet. His insights emphasize the evolving understanding of celestial mechanics and the public's fascination with the obscure. Tyson argues that Pluto's reclassification is not a demotion but rather a reflection of our growing awareness of the numerous bodies orbiting the Sun. His approach to celestial mechanics embodies a spirit of ongoing discovery and adaptation. He sees the complexities of Pluto's orbit as evidence that there is still much to learn about space. Interest in these inquiries, especially the potential interactions between Neptune and Pluto, underscores the dynamic and often unpredictable nature of our solar system. Tyson's work suggests that the more we uncover about space, the more questions arise, driving further investigation and expanding our comprehension of the universe. Another renowned physicist, Michio Kaku, offers a complementary perspective on the mysteries of space. Kaku is known for making intricate scientific concepts accessible and integrating visionary ideas into discussions on celestial mechanics. His views on Pluto and its orbit emphasize the necessity for advanced observation and continuous modeling to make accurate predictions and understand potential celestial events. Kaku regards the interactions between celestial bodies as a crucial area of study, not only for practical purposes but also for academic interest. For instance, the potential collision between Pluto and Neptune is not merely a theoretical scenario. It serves as a reminder of the dynamic and often turbulent nature of space. His futurist outlook encourages us to consider the broader consequences of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His perspective underscores the importance of being prepared for the unexpected in space. According to Kaku, the more we comprehend the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of astronomical occurrences. Both Tyson and Kaku converge on the idea that space is a realm of endless exploration. While our current understanding is substantial, it remains limited. Their emphasis on ongoing inquiry and advanced modeling reflects the evolving nature of space science. They highlight the significance of not only understanding celestial mechanics as they exist today but also speculating on how they might change in the future. The possibility of a collision between Pluto and Neptune serves as an example of larger concerns and opportunities in space exploration. It highlights the necessity of scientific rigor, cutting-edge technology, and a willingness to adjust our understanding as new information emerges. For both Tyson and Kaku, the mysteries of space, illustrated by Pluto's orbit, call for action from the scientific community and humanity as a whole. There is a general scientific consensus that, for many years to come, Pluto and Neptune's orbits will remain stable due to their mean motion resonance and the various gravitational forces acting upon them. Thus, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential subtleties of orbital dynamics suggest that cosmologists should continue monitoring and studying these celestial bodies. Doing so will enhance their understanding of long-term behavior and any potential risks they may pose. While the likelihood of a Pluto-Neptune collision remains largely hypothetical and is considered unlikely based on current knowledge, it underscores the importance of ongoing investigation and observation. Advancements in space science and technology, including more sophisticated telescopes and virtual simulations, will aid astronomers in refining their models and forecasts. This will ensure that we remain informed about the dynamic and ever-evolving nature of our solar system.